All right, welcome to today's review session. We're going to be covering momentum. We're going to be covering momentum. All right, there are a slew of learning objectives talking about momentum. I just want to quickly walk through these just so you guys are aware of them, and then we'll move on for the rest of the talk. All right. So again, the plan is go over the learning objectives, give you some time to work on some practice problems, or we'll cover kind of briefly outline momentum, what it is, let you work on some practice problems. Go over the practice problems, and then if we have time at the end, we'll open it up. I know you guys probably want to ask questions about the multiple choice test, so we can go over a couple of those if you'd like. For right now, the student is able to make quantitative predictions about the natural phenomena based on conservation of linear momentum and the restoration of kinetic energy in elastic collisions. So what this means is that linear momentum is always conserved, and kinetic energy is only conserved in an elastic collision. All right. And when I say I mean a perfectly elastic collision. All right. Now, if energy is not conserved, that means it's going to be inelastic. Now, what does that look like? I think this may have been kind of a little bit of a misconception here. Is that unless it's perfectly elastic in that it hits and it bounces, we will then call it inelastic. So even though the perfect inelastic collision hits and sticks, an inelastic collision technically could hit and bounce as long as it's not perfectly bouncing. In other words, if like a car hits another car, crumples, so you lose energy to that crumpling, and then bounces off a little bit, that's technically inelastic, because you are still losing energy. So rather than thinking of it as bouncing or sticking, think of it as elastic, kinetic energy is conserved, inelastic, kinetic energy is lost. And in an explosion, kinetic energy would be gained. Alright, so let's keep going. I think we'll hit on that throughout here. Students able to apply principles mentioned up here to reconcile a situation that appears to be isolated and elastic, but in which data indicates that linear momentum and kinetic energy are not the same after interaction. Okay, so in other words, there's something that looks like it should be an elastic collision, but upon looking at the data, you see that momentum and energy are not conserved. All right. By refining scientific questions to identify interactions that have not been considered. All right. So if you like bounce a ball, right, and you find that the energy is not conserved, well, what else? Like, where could have you lost energy, right? So maybe think about how could you analyze where the energy was lost, where was the momentum lost? Was there another piece moving? Did something fall off, et cetera, et cetera. Students will be expected to solve qualitatively and or quantitatively for one-dimensional situations and only qualitatively in two-dimensional situations. So remember all those big problems I did were two-dimensional collisions? You just need to know those qualitatively, not quantitatively. So you should be able to understand quantitatively, in other words, like calculatory, everything to do with a one-dimensional collision. Right? I think everyone in here could do that. And then qualitatively, you need to know about when things hit and they go off in two dimensions. Right. That was a big one. Students apply mathematical routines appropriately to problems involving elastic collisions in one dimension and justify the selection of those mathematical routines based on conservation of momentum and restoration of kinetic energy. So, if I give you a problem and say, all right, this problem is perfectly elastic, you should be able to use that information to solve for the rest of that problem. So by using the two equations, right? Momentum initial equals momentum final. Total energy initial or kinetic energy initial equals kinetic energy final. So you should be able to use that with elastic collisions. Students able to classify a given collision as elastic or inelastic. Justify the selection and conservation of linear momentum and restoration of kinetic energy as the appropriate principles for analyzing an elastic collision. Solve for missing variables and to calculate the variables. So, given a collision, you should be able to say, is it elastic or inelastic? And then, kind of like what was just mentioned up here before, you should be able to solve for all the variables in those problems. The student is able to qualitatively predict, in terms of linear momentum and kinetic energy, how the outcome of a collision between two objects changes, depending on whether the collision is inelastic or elastic. I think that seems pretty straightforward. If you see here's a collision, this is what happened. All right, now that collision is, rather than being inelastic, okay, now it's elastic. What changes? All right, so kind of think about that. I think that's pretty simple for you guys to do. The student is able to apply conservation of linear momentum to a closed system of objects involved in an inelastic collision to predict the change in kinetic energy. So this is like that one out of the, I believe we had it on the momentum test, where you had the graph, right, of the object before the collision and it drops down to after the collision. You should be able to identify that situation. The student is able to classify a given collision situation as elastic or inelastic. This is the same one. Okay. Yeah, okay, cool. I guess this is more on the fact that as the appropriate solution for method of inelastic collision, recognize that there is a common final velocity. Okay, so for an inelastic collision now, you should be able to identify that when they collide and they stick, there's going to be a common final velocity. All right. Students able to analyze data to verify conservation of momentum in a collision with and without an external friction force. So is momentum conserved when there's friction? No. All right? Because again, everything, this whole idea of conservation of energy, conservation of momentum, conservation of angular momentum, all this hinges on if there's an external force or not. If there's an external force, then it's not conserved. Otherwise, it is conserved. All right. Kind of continuing on here, we talk about impulse. This one has a lot of objectives, so just be ready for it on the test. The student is able to justify the selection of data needed to determine the relationship between the direction of force acting on an object and the change in momentum caused by that force. All right, so impulse is F delta T, right? And so remember, for every action, there's an equal and opposite reaction. So for every collision, there's going to be an equal and opposite impulse acting on both objects involved in that collision. And so you should be able to identify the direction of the impulse and direction of the force. The student is able to justify the selection of routine for the calculation of relationships between changes in momentum of an object, average force, impulse, and time of interaction. So just be able to solve for anything involving F delta T, or the FAT-MAV equation, or delta P, all that stuff. The student is able to predict the change in momentum of an object from the average force exerted on the object in the interval of time. Right? So you should, again, just be, and that's probably going to be in the form of a graph. And so you should know that the area under a force-time graph is going to be the impulse. All right? The student is able to analyze data, et cetera, et cetera. Students able to analyze data to find the change in linear momentum for a constant mass system using the product of the mass and the change in velocity of the center of mass. All right, now, one thing I do want to bring up is the idea of center of mass. Center of mass. All right. The idea is that if you have a system and you close out the system and you have multiple objects in that system, let's say you have a cat and a dog floating around in this system, right? The cat and the dog can be doing whatever they want, right? But their center of mass must always have a constant velocity unless there's an external force involved. All right. Another way to think about this is if you're floating around in space. Right, let's say you're floating around in space. You're on the International Space Station, and you start going like this. Are you going to go anywhere? No, you're not. Because it doesn't work like it does in the cartoons, right? If you're going like this, you can't swim through empty space because regardless of what you're doing, your center of mass is still like here. I think it's the human center of mass. All right, and that velocity is not going to change because there are no external forces acting on you, the system. Does that kind of make sense? So in order to change your velocity, you need an external force. That's kind of what that's hinting at again. The student is able to apply mathematical routines to calculate change of momentum of the system by analyzing the average force over a certain time. That's the same thing. The student is able to perform analysis on data presented as a force-time graph and predict the change in momentum of the system. Right? The student is able to calculate the change in linear momentum of a two-object system with a constant mass in linear motion from a representation of the system. Right? So So even if you have a two-object system, if they like collide with each other or they bump into each other, something like that, the overall combined momentum will remain the same. So kind of hinting at conservation. But that was a lot of objectives. Are there any questions on those? Okay. So basically, what's going to be on here for momentum is you have to know P equals mv. You have to know that impulse is equal to the change in momentum. You also need to know m delta v equals f delta t. Remember, this is kind of like the first half of our momentum unit was just this. All right? But then we had to talk about collisions too. Now collisions, let's see, is this on the camera? Here we go. All right. So collisions were the next part of it. All right. So you have to know elastic versus inelastic, and that with elastic energy is conserved and inelastic energy is not conserved. All right. You then would have to know that P initial equals P final. Now let me just backtrack here. Energy is conserved in elastic, not conserved in inelastic. But in both cases, assuming there is no external forces, the initial momentum is always going to be equal to the final momentum. And so if you have multiple objects, you end up with m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. And from here, you should be able to solve for any of the missing variables here. All right? But also be ready to look at graphs, too. Kind of going back here, if you have a force time graph, the area equals the impulse. All right? And so with this, I mean, it seems like we're kind of on the right track here, so I'm going to turn it over to you guys now. I'm going to give you maybe about 15 minutes or so, 20 minutes. I want you to try and work on the two free response sections out of the book. All right, so let's go ahead, turn to, what page were they on, Jess?
130.
I mean, unknown student? 130?
Yeah.
Thank you, unnamed student. Okay, yeah, so if you turn to page 130, you have your two free response questions. I want you to try and knock those out, and then when we get back in about 20 minutes, we'll go over them. All right. If you get done with it early, go and work on the multiple choice section. All right, we're going to go over number 1 here really quick, and then we'll let you work on number 2. So for this one, I was asking you to find the tension in the string, which is odd because they're asking you to find the tension before they've covered the unit on centrifugal motion, and rotation, which is fine, but we're just going to go over that right now. We have covered centrifugal motion, so we should have no problem with this. We can't find our marker now. All right. So as you can see, the free body diagram looks like this. We have tension going up and to the right, and we have gravity straight down. All right. Now we broke gravity into components, Fg1 and Fg2. Now through the magic of geometry, we can see that this angle here in purple is equal to this angle here in black. All right, because they're similar triangles, and so everything ends up working out just fine there. And so what we end up doing is see, all right, this green Fg1 here is going to be equal to Fg sine theta, right? Because it's opposite of that divided by hypotenuse. It's a sine, so opposite equals sine times hypotenuse. And so now that's going to be Fg1. Then we have Ft. We're trying to solve for Ft here. All right. Now, which is going to be greater, Ft or Fg1? What do you think? Ft. And the reason why is because it's accelerating towards the center. It's undergoing centripetal acceleration. As we end up saying that F net equals Ft. Let me just keep the same colors here. Ft minus Fg1. All right. Now we know that Fnet is equal to Ma. But what type of acceleration is it? Centripetal. So we get m times a, which is just v squared over r, equals Ft minus Fg1. Alright? Now, they go ahead and they use conservation of energy to get the velocity and all that junk, but you don't need to do that in the book. Really, it's asking you to solve for Ft, so I say just solve for Ft. Ft equals Fg1 plus mv squared over r. Thanks. That's all you got to do. Alright? Does that make sense? Right, now, why did they have you solve this? I'm not really sure, but hey, they did it. So, next is asking you now, alright, it goes ahead and collides with a block. Alright? Now, the collision is elastic. Alright? So that means, yes, you have to use conservation of momentum and conservation of energy in order to get that answer here. Alright? So, first off, let me erase this, because I don't want to redraw all that. What is the initial velocity before the collision of the pendulum? How do we go about solving? What should we use in order to solve that? Conservation of what? How do we get the velocity down at the bottom of the swing? Of energy, yes, conservation of energy. And so we know what type of energy do we have up here? Potential. What type of energy do we have down here? Kinetic, right? And it's conserved because there's no external forces in our system. Alright? And so that means that we end up with mgh, and what's the height again? That's going to be L, right? mgl equals 1/2 mv squared. So let's go ahead and solve for v, and we can then go ahead and get the that velocity before the collision. Alright, so the m's cancel out, and we end up with v equals square root 2gl. Alright? And so, how do we get the speed of the block immediately after the collision? Well, we set it equal to each other using conservation of momentum. We get mass of the pendulum times velocity initial of the pendulum plus mass of the block times velocity initial of the block equals mass of the pendulum, velocity of the pendulum final plus mass of the block, velocity of the block final. You guys see how I set that up? Now, what are we trying to get? We're trying to find the speed of the block immediately after the collision. So we are looking for this. In fact, I'm going to write this in red. That is our goal. Alright? Now we know the initial velocity of the pendulum is root 2gl. Alright? And we know what's the initial velocity of the block? 0. Alright? But we still have two unknowns. We don't know the velocity of the pendulum after the collision. We don't know the velocity of the ball after the collision. But we do know that it's elastic. Alright? So, we know that energy is conserved. Alright? So we can create another equation to have our second equation, and we can plug them in and solve. Alright? Hang on here. Let me just get something out of this real quick like. What chapter is this? 7? Yeah, what number was it? Thank you very much. Alright. Okay, great. Great. Cool. Oh, this is done before. Oh, that's done. Okay, good. So, let's go ahead and set this up, conservation of energy. So, we have it swinging down here. We say that before the collision, this guy has energy and the block doesn't. But so we're going to do E. Get it back in U now. So we say EK of the pendulum initial plus EK of the block initial must be equal to EK of the pendulum final plus EK of the block final. Alright? Now again, the block has no initial kinetic energy and no initial momentum. So, that gets us 1/2 mass of the pendulum times the velocity of the pendulum squared equals, see here, 1/2 mass of the pendulum, velocity of the pendulum final squared, plus 1/2 mass of the block, velocity of the block final squared. Alright? So that seems like a lot. It kind of is. But what you can do is you can then solve for one of your unknowns, plug it into here, to eventually get that VB prime. Alright, so it seems like a lot of algebra, but really it's not too bad because you know that all these 1/2s cancel out. Alright. Do they have the same mass? No. But you do know one is 4m. Right? It says the block here is 4 times the mass. Alright? So you can cancel out these 1/2s, and we can start to rewrite this. So I'm going to do that here. Finish up this algebra here. Knock this out really quick. So now we got 2 equations. Let me just rewrite these equations here nice and neat. So we have mass of the pendulum is just m. Yeah. Alright, so really quick. M times root 2 GL plus 0 equals m times velocity of the pendulum, Vp prime squared, plus 4m, alright, times our main unknown, which is going to be Vb prime. Alright, now we can cancel out all the m's, and we now go on to the other equation. So we then get m times square root 2gl squared equals m times Vp prime. Yep.
So wait, the 2gl is the pendulum velocity?
Right, which is what we got right here, using conservation methods. That's the initial pendulum velocity.
Then you plug that into
the Vp, not the Vp. All right. Okay. So, so we're looking for Vp prime. Or no, we're not. We're looking for Vb prime and my marker, which is right here. Plus squared plus 4m times Vb prime squared. All right. Again, all the m's cancel out, and this actually just squares to 2gl. So what I'm going to do here is I'm going to solve for Vp prime and then plug it into the initial equation. So we end up getting 2gl equals Vp squared plus 4Vb squared. So I bring that over, I subtract it over, and so we get Vp equals the square root, all right, of square root of 2gl minus 4vb squared. And I take this, I plug it into the initial equation here, this is Vp prime. And so then we end up getting 2gl square root equals square root of 2gl minus 4vb squared plus vb prime. So you get this whole elaborate thing, and you can solve for vb prime from here.
Wait, what did you just plug that into?
I took this, and I plugged it into that. And so now I got rid of both my unknowns. I can bring that over. You could square both sides, get that all taken care of. All right. This algebra is pretty intense. I cannot imagine you guys seen all the different practice problems. This is not going to be the type of algebra you're going to be doing on the test. All right? All right, but the concept is one I want to make sure you get. In order to solve an elastic collision problem, you have to first use conservation of energy, and then use conservation of momentum, and to get your two unknowns disappearing. All right. To what height will the ball rebound after the collision? Do you guys have an answer to that you want to submit? All right. Okay. Basically, it's going to rebound to a height lower than initially it was. So where does that change in energy go? Where did that rest of the energy go?
Into the block.
Yeah, into the block. So it lost energy into the block, so it does not rebound back to the same height. To find the exact height, again, you're not going to do this on the test, but you take that VD prime and set that energy, find the energy of the block, and then subtract that from the potential energy that you started with, and from there you can then calculate the final potential energy and go.
So there could just be like a question saying like.
My guess is that you wouldn't have something this intense. It would be just a very conceptual question. Like, what were you going to say?
Like, where would the height be? And you would just have to say it's lower because the energy goes in.
It would be lower because energy is lost into the block. You will not have to use this crazy math like that. Alright, so what I want you guys to do now is try and work on number 2. I'll take another like 5 minutes here to work on number 2, and we'll go over it really quick and we'll call it a day. Okay? Alright, so really quick, a quick example that does not involve the crazy algebra is you have, rather than doing with a pendulum, let's just say you have bumper cars here. So this is initial, this is final, all right? You have these bumper cars. This guy is going this way, this guy is going this way. Let's say this action is initially at rest, v equals 0. V equals, we'll say, 2 meters per second positive. All right? We'll call this car A, car B. They collide elastically. Find the velocity of car A after the collision. And the direction. We'll say that B has 4 times the mass of A. Right, so B has 4 times the mass of A. When they collide, what is the velocity of A? So, let's go solve this really quick, and then I'll let you guys get out of here. So, basically what you gotta do is you gotta set up 2 equations. The first one is going to be momentum. So we end up with m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. So you start off with 2 is your velocity for A times the mass of A, which is just m, plus 0 equals the unknown velocity, so there's still m, so m times va prime plus 4m vb prime. Alright, a couple things you can do now is you can cancel out all the m's. So you end up with 2 equals va prime plus 4 vb prime. And now what I recommend doing is solving for one of your unknowns. So we get va prime equals 2 minus 4 vb prime. Does that make sense? How we did that? That was kind of quick, I know. All right, now, so that was for momentum. Let's look at energy. So energy, we have 1/2 mv squared plus 1/2 mv squared equals 1/2 mv v prime squared plus 1/2 mv prime squared. The reason why we're doing this is because it's elastic, so we know energy is conserved. All right. So we end up getting 1/2 m times 4, right? Because that's 2 squared. Equal or plus 0 equals 1/2 mva prime squared plus 1/2 4m vb prime squared. You see how I set that up? All right, all the m's cancel out. Again, so we end up with 2 equals 1/2 v a prime squared plus 2 v b prime.
Wait, why don't the 1/2s cancel out? Can you decide
Oh, they
that?
do. No, they do.
Yeah.
And then, so if you cancel the 1/2s, you would have 4 equals va prime squared plus 4 vb prime squared. All right, and so that would work too. In fact, let's do that. Let's do that. That might be easy. So I'm going to 4 equals that plus 4. Okay, cool. Actually, that works out a lot easier. So we'll just cancel. Well, I mean, you should get the same answer either way, but this makes it a little easier. So now we got 2 equations, 2 unknowns, substitute and solve. Does that make sense? Let me just walk you through that really quick. So we end up with 4 equals VA, so this is plug VA right here. And so we get then 2 minus 4 VB prime squared plus 4 VB prime squared. Alright. So now to solve out the algebra here, you just got to FOIL out that binomial. So you end up getting, maybe what, 4 minus 16 VB prime plus positive 16 VB prime squared. And then you plug in, you solve for the quadratic and you're good. There might be a program I think you can download on your calculators that allow you to just plug in like the coefficients and solve for the quadratic. But so your final quadratic should look like this, where you get 4 equals 4 minus 16 VB prime plus 16 VB prime. All right, plus your 4 VB squared. So you simplify this out and you end up with, you can divide everything by 4. This way, so you're left with 0 equals negative 4 VB prime plus 5 VB prime squared. There you go.
Did you subtract the 4 first?
Yeah. I did minus 4 minus 4. Brought that over. And then I added this to get 20. And those two together, and you divide it both by 4. And there you go. And so then you just solve for that quadratic there, which was it negative b plus or minus squared, root of 4. B squared minus 4ac all over 2a. Okay.
I see.
So you do that, and you get bb.
Okay.
I'm not going to do that in my head.
I figure out.
Alright. So that would be how you solve a perfectly elastic collision with nothing but algebra. Does that make sense? Kinda. I'm sorry we took up the entire time just answering this one question. That's again why I don't think it'll be on the test, because it takes forever to do this, and that'd be a lot of time. And they know that. Alright, so really quick there was one multiple choice if you want to talk about. And then I promise I'll let you go. It was, where is it?
Where'd you get the 5 VB squared from?
By doing 20 VB squared, by adding these together. And then I divided the whole thing by 4.
Oh, okay.
I just factored out 4 out of it. So you also think it was just 4 VB squared plus 1 VB squared. We divide everything by. And it was number 3 here, number 3. I just want to make sure we understand the fat MAV equation. All right, so can everyone look at number 3 on page 128? So a box of mass 2 kilograms accelerates in a straight line from 4 meters per second to 8 meters per second due to an application of force whose duration is 0.5 seconds. Find the average strength of this force. So this is just the fat MAV equation where you set m delta v to delta v, your increasing velocity from 4 to 8, so it's going to be positive 4 is your delta v, mass is 2, so your MAV is going to be 8. See you later. And so then you get 8 equals, so you get m delta v equals f delta t, so you get 8 is f times 0.5, so f is 16, which is d. So like this is the majority of what it's going to be like here. The other thing you might run into is graphing. You might run into oh, here's one. If we do conceptual two-dimensional collision, basically it's just saying that you have like billiards, and this guy's going here with some velocity. This has velocity equal to 0, right? And they collide. They're gonna kind of scatter in all different directions, right? So this is before, this is after. They're not gonna be going like that, right? But the main thing you have to know here, main thing, is that P initial, so Pi in the x direction and Pi in the y direction equals Pf in the x direction equals Py also in the final. All right. So what does that mean? Well, initially we have a momentum of 0 vertically and some momentum horizontally. We have like m and m, right? So this is equal to 0 and this is equal to mv. That means that this is equal to mv and this is equal to 0. Now how can that equal to 0 if they're both all moving in vertical components, right? Because if you break these down, you see that you have px's and py's here. Well, basically what it's saying is that this vertical one has to cancel out that vertical one. In other words, they're equal and opposite. Does that make sense? That's kind of the main conceptual thing with two-dimensional. Also, when you add up this mpx, or the horizontal velocity and the horizontal velocity times the masses of the two, they should come back and equal m. And you won't have to do anything qualitative-wise, just quantitative. Other way around. You don't have to do anything quantitatively, I'll be qualitative. So, again, I apologize that the majority of this review session was just solving that one problem. So, in future review sessions, I'll make sure to break it down a little bit quicker. But, do you guys have any other questions for me? Okay, cool.